Science in Action 26, the Nazari Bone. The Alhambra of Granada does not only constitute the crowning moment of the Nazari architecture, but it is also a valuable scientific contribution that comes from its architects' concern about the decoration of each space, no matter how small it was. On today's experiment, we are going to approach the Nazari Bone, the most famous mosaic that, through its mathematical transformations, caused the splendid figures the walls of the Alhambra harbor. We are going to present another mathematical experiment. In order to introduce it, we are going to make use of one of the mosaics in the Alhambra. We are going to verify that if, with great skill, we rearrange a geometric figure, we will obtain a figure with the same area. We get the Nazari bone by cutting a square into pieces and recomposing the figure of the square. And the Nazari bone fits in, forming one of the same mosaics. The property of the area preservation is maintained, which in the pieces, the area preservation was maintained. Making use of this same effect, we can build a paradox, the ball paradox, where the sine attribute is not fulfilled. We start from an 8 by 8 square, 64 squared area. We are going to see that, on changing the pieces, it doesn't maintain the area. Apparently, as we have just proved that it had to maintain the area, we enter into a contradiction. But if we count them, we have a rectangle of 13 by 5, which are 65 little squares. Where does that extra square come from? We are going to see whether mathematics can explain us this paradox. We pay attention to the size of the squares, the choice of the numbers has not been arbitrary. That is to say, we are doing an approximation. The pieces will then fit together correctly. And if the pitch of one of the straight lines is 3 out of 8, the other will be 2 out of 5. That is not the same. We can see that little approximation visually, and that will be the explanation. But the most interesting part of this paradox is that the used numbers in order to solve it are the Fibonacci numbers. We are using the elements of this sequence. It was Kepler, as we are in the science park, who realized that they fulfilled a property. The quotients of the sequence tend to a mathematically important number, the golden ratio, as much for the art as for the nature. If we elevate a number of the sequence to the second power, 8 squared in this case, the result is very similar to the product of the former elements. In this case, 13 times 5.65. The difference between the two results is 1, the little square we had when moving the pieces.